In this video, we're going to look at a technique of integration known as numerical integration. And I say technique, I actually mean there are three techniques specifically that we will examine. Now, numerical integration is used for functions whose antiderivative has no closed form or whose closed form cannot be expressed easily. As an example of this, if we look at the integral minus 1 to 1 of e to the negative x squared over 2 dx, right? The function e to the negative x squared over 2 has no analytic antiderivative, right? You cannot find it. So in order to evaluate this integral, we have to use a numerical technique, right? So numerical techniques simply provide approximations for the true value of the integral. Three we will study in this video. The midpoint rule, the trapezoidal rule, and finally, Simpson's rule. Of the three, the midpoint rule is the simplest, as it comes from the midpoint approximation when we studied the area problem back in Calculus 1. What we do is we assume f of x is continuous on the closed interval AB. We then divide AB into n subintervals of equal length. Call them delta x, which is b minus a over n. Then we can approximate the integral from a to b of f of x dx as, and here's the rule, m sub n is equal to delta x times f of m1 plus f of m2, so on and so forth, plus f of mn, which will also be written this way, delta x equals the sum I equals 1 to n, f of m sub I. I don't know why I put an equals there. That should be multiplication. Delta x times, where m sub I is defined to be a plus I minus a half delta x. And this is the midpoint of the ith subinterval. Hence its name, midpoint rule. As an example, let's go ahead and evaluate m4 for the integral 0 to 1 of x squared dx, right? Now this serves as a good example because we obviously know how to find the exact value for this integral. Right? So you'd be able to look at how good of an estimate M4 really is. Okay. Well, first thing you want to do, let's do all this in blue, right? Let's find delta x first. Right, so remember delta x is b minus a over n. All right, so delta x is a quarter. And f of x itself is x squared. Okay. Let's write out the endpoints of each subinterval. X naught always starts at a, so x naught will be 0. Next endpoint would be x1, which is a quarter. Then x2 would be a half. x3 would be 3/4. And xn, so in this case x4, always is our ending point b, which is 1. So notice that all we did, right, we started x0 equals a, and then added delta x until we got up to b. Right, therefore our M4, remember, is delta x times the summation I equals 1 to n f of m sub I, but m sub I was a, which is 0, plus I minus a half times delta x. All right? So what we're going to have here is 1/4 summation I equals 1 to 4 f of I over 4 minus 1/8. What we'll do is now go and look at putting this into our calculator. And here we are at our calculator, right? So first thing we want to do is let's go ahead and define f of x. As x squared. Right? So remember, f of x is our integrand. There you go, now it's stored. Now we want M4, so that is a quarter times a summation. To do summation, we go to menu, calculus, sum. Right? Our index is I, so we go I equals 1 to 4 f of, and we said it was I divided by 4 minus 1 divided by 8. Now we want an approximation, so let's come back over to one of these. Let's say this 8. Let's put a decimal there just so we get an approximation. Hit enter, and we get 0.328125. Right, so M4.328125, meaning that this integral, we can say, using M4 is approximately 0.328125. That's what we just did. And I'll leave it to the viewer to actually evaluate the exact value of the integral and see how good of an estimate this was. Okay. Now, let's look at the trapezoidal rule. Okay. Now, when we were studying Riemann sums, Right? We form these sums by using rectangles. However, there's nothing limiting us to just using rectangles. So, for example, we could use trapezoids. Right? As in this figure. Stop that. Thank you. I apologize, my mouse is acting up. There we go. Right? Now, we proceed similarly, right? So what we do is divide the interval AB into n sub-intervals of equal length delta x equals b minus a over n. We form the trapezoids by joining the points x naught, y naught, x1, y1, so on and so forth, up to xn, yn, with line segments, as shown in the figure above. All right? Now, area of a trapezoid. All right? Specifically, area of our ith trapezoid is given as 1/2 delta x, right, base, times y sub I plus 1 plus y sub I. So it's 1/2 the base times the sum of the lengths, of the height, right? The two other sides, right? So 1/2 base times the sum of this height and this height. That is area of a trapezoid. Well, then the total area would be the sum of all these areas, right? We call this T sub n. That would be the sum of all the AIs, right? Well, if we take a look, what we get is this. Let's do this on the next line. A1, 1/2 delta x times y2 plus y1, then plus 1/2 delta x, y3 plus y2. I'm sorry. We start No, I was right. I equals 1. However, I, for some reason, wrote this as I plus 1. My apologies. This should have been y sub I minus 1. So start over from here. This would be y naught plus y1. Then plus 1/2 delta x, y1 plus y2, plus so on and so forth, plus 1/2 delta x, y sub n minus 1 plus y sub n. If we group terms together, notice we get a half delta x, that's common, times, right, we have a single y naught term. Notice we're going to have two y1 terms. We'll have two y2 terms. We continue this way, we're going to have two yn minus 1 terms, and then just a single yn term. Right? So this is our rule. Again, we assume f of x is continuous on AB if we divide AB into n subintervals of equal length, delta x equals b minus a over n, then we can approximate the integral from a to b of f of x dx as t sub n, which equals 1/2 delta x times y naught plus 2y1 plus 2y2 plus so on and so forth plus 2yn minus 1 plus y sub n, where the y sub I is equal to f of x sub I. Right? Notice it's called the trapezoidal rule because we used trapezoids to approximate the area. As our example, we'll consider the same integral, except this time we will evaluate T4. So again, start with delta x, which was b minus a over n. F of x, again, is x squared. Write out our endpoints, so 0, x1 is a quarter, x2 is a half, x3 is 3/4, and x4 is 1. Then T4, 1/2 times delta x times f of x naught plus 2 times f of x1 plus 2 times f of x2 plus 2 times f of x3 plus finally f of x4. So that is 1/8. Now notice what we have. F of x naught plus f of x4 plus, now these remaining three all have a scalar factor of 2, so let's go I equals 1 to 3 f of x sub I. But f of x sub I we can rewrite. Right, so x0 is 0, x4 is 1, summation I equals 1 to 3, 2 times that. F of, so x sub I would be 0, a, plus I times delta x. Right, so in context for us, it is I times delta x, so just I over 4. This form is going to make it easier for us to use our calculator. So back over at our calculator, there's no need for us to re-enter f of x, right? It's already defined. So now what we have is 1/8 times, oops, I'm sorry, I don't need that yet. We said f of 0 plus f of 1 plus 2 times, now we need the sum. We said it was I equals 1 to 3. F of I divided by 4. Again, I'm going to put a decimal just so I get an approximation. Let's evaluate that. And we get 0.34375. Right, so again, what we did was we said that this integral was approximated using T4, which was 0.34375. So using trapezoid rule with 4 subintervals, we found the integral from 0 to 1 of x squared to be about 0.34375. For Simpson's rule, we replace the line segments from the trapezoidal rule with parabolas instead, as shown in this image. This allows us to obtain an approximation that is usually substantially more accurate than either the trapezoidal rule or the midpoint rule. All right, so as before, divide the interval AB into n subintervals of equal length delta x equals b minus a over n. This time, however, we add the stipulation that n must be even. Now what we do is pair up the resulting intervals. That is, the interval x0 to x1 gets paired up with the interval x1 to x2. Right, then the interval x2 to x3 gets paired up with the interval x3 to x4, so on and so forth. Now, for each pair of intervals. We want to find a parabola that passes through the 3 points on the curve above the endpoints and the 2 intervals. Then we will take the sum of the areas that are under the parabolas as an approximation to the area under the curve. We begin with the pair of intervals negative delta x to 0 and 0 to delta x, centered around the origin. Assume that the corresponding 3 points are P naught equals delta x y naught, P1 is 0y1, and P2 is delta x comma y2. Right, now, recall general equation for a parabola is ax squared plus bx plus c, or I should say y equals that. Right? Where a, b, and c are all real numbers. Okay. Now, the area under this parabola is obtained by integration. Right? It's the integral from negative delta x to positive delta x of ax squared plus bx plus c. And that is a over 3x cubed plus b over 2x squared plus cx, where x goes from negative delta x to positive delta x. With some algebra, we get this is 2 times a delta x cubed over 3 plus c times delta x, which will simplify out to delta x over 3, 2a delta x squared plus 6 times c. However, note, we also have to have this. Y naught has to be a times delta x squared minus b times delta x plus c. Y1 has to be just c, and y2 has to be a times delta x squared plus b times delta x plus c. Right? This comes from the fact that we have our general equation for parabola here, and we have the 3 points P0, P1, and P2, which have to fall on that parabola, right? So these points have to satisfy that equation. Let's label these equations 1, 2, and 3. If we take 1 plus 3, look at what we get. Y naught plus y2 is equal to 2a delta x squared plus 2 times c. Now, if we add 4 copies of the second equation, to this, right, we will get y0 plus 4y1 plus y2 has to be 2a times delta x squared. And please forgive me, I put that squared in the wrong place. There we go. Plus 6 times c, right? Well, look, that, right, this is this. So we just do substitution. So the area winds up being delta x over 3 times y0 plus 4y1 plus y2. Notice that this area depends only on the y coordinates of the 3 points. So we can obtain a similar expression if we cite the parabola over any of the subsequent pairs of adjacent subintervals. So what we're going to get is total area delta x over 3, y0 plus 4y1 plus y2 plus delta x over 3, y2 plus 4y3 plus y4, so on and so forth, until we add delta x over 3, yn minus 2 plus 4 yn minus 1 plus y sub n. Algebraically simplifying this, we will wind up with Simpson's rule. As with the previous two, we assume f of x is continuous on the closed interval AB. Right, so if we divide AB into n subintervals of equal length, delta x equals b minus a over n, then we can approximate the integral from a to b f of x dx as s sub n, and I should specify here that n is even. All right, then we get Sn equals 1/3 delta x times y0 plus 4y1 plus 2y2 plus 4y3, so on and so forth, plus 2yn minus 2 plus 4yn minus 1 plus y sub n. And again, y sub I is f of x sub I. Right? And as our example for Simpson's rule, you guessed it, we'll use the same integral. So we will evaluate S4 for the integral 0 to 1 of x squared dx. Oops. Right? So delta x, right, again will be a quarter. F of x will again be x squared. X0 is 0. X1 is a quarter. X2 is a half. X3 is 3/4. And finally, x4 is 1. So S4 will be 1/3 times delta x. Now, f of 0 plus 4 let me not do 0 yet. I'm going to do f of x naught plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3 plus f of x4. Right, so we get a 12th times, now notice, we get f of x naught, so f of 0, plus, we get a single x4, right, f of 1, plus now all of the odd indices I'll multiply by 4, so let's do this. I equals 1. How do I want to do this? I equals 1 comma 3. I'll write it that way. F of x sub I plus 2 times f of x2, which was a half. I'm trying to think of the easiest way to put this in a calculator. Yeah, you know what? I think I'm going to do it this way. I equals 2. Right, but x sub I we already know. Right, it is I times delta x, so I over 4. And now we'll go over to a calculator to enter this. So after playing around with the calculator, I'm going to rewrite these sums. I'm going to write it this way. Right, so 4 times, I want I to go from 0 to 1, right? Because we need x1 and x3, that's 2. So 0, 1, that's 2. F of, something times delta x. Well, since we're only dealing with odds, let's call it 2i plus 1 times delta x over 4. Right now, for the evens, let's just go I equals 1 to 1, because there's only one of them. F of 2i over 4. Okay, so over at our calculator, let's go ahead and enter everything in. So we have 1/12 times f of 0 plus f of 1 plus now we have 4 times, we need menu calculus sum, I equals 0 to 1, f of 2 times I plus 1 over 4, plus now 2 times the sum of all the evens, right? So menu, calculus, sum, I equals 1 to 1, f of 2 times I over 4. And if we hit, let's put a decimal point after that last 4, hit enter, and we get 0.3 repeating, so 1/3. Right, so what this is saying is we approximated the integral 0 to 1 of x squared dx as S4. Got it as 0.3 repeating, which is 1/3.